Welcome to this explainer. Okay, so today we're diving straight into the really fascinating world of computer hardware. Now, whenever we think about upgrading our devices, we usually want three things, right? We want it to be blazingly fast, we want it to hold a massive amount of data, and ideally, we don't want it to totally empty our wallets. But in the world of computer engineering, you can rarely have all three at once. Designing a computer is basically a massive, high-stakes balancing act between speed, capacity, and cost. Take a look at this. Welcome to the machine. It looks like a glowing, intricate little cityscape, doesn't it? Well, this circuit board represents the incredibly complex physical components that power our entire digital lives. Every single pathway, every chip, every tiny cylinder you're seeing is a physical manifestation of that engineering balancing act we just talked about. To really grasp how our devices work, we have to look way past the sleek outer casing and understand the traffic flowing through this digital metropolis. Here is our roadmap for today's explainer. 1. The hardware balancing act. 2. Primary memory, RAM, and ROM. 3. Managing traffic and embedded systems. 4. Secondary storage solutions. And 5. Bringing data to life. All right, let's jump into Section 1, the hardware balancing act, speed versus cost. Like I mentioned, computer design is fundamentally a series of really clever engineering compromises. You literally can't build a computer using just one type of storage component, mostly because the physics and the economics just won't let you. Just look at this memory hierarchy. The register, which lives right inside the CPU, is the absolute fastest memory there is, but it's tiny. Then we step down to cache memory, which is also incredibly fast, but still pretty limited in size and honestly quite expensive. As we move down to main memory, capacity goes up and the cost per byte drops, but your speed decreases. And finally, we hit secondary storage, like your hard drive. It's the slowest of the bunch for sure, but it gives you massive capacity at the absolute lowest cost. So we're basically trading speed for capacity and affordability the further we move outward from the processor. Moving right along to Section 2. Primary memory, RAM, and ROM. So think of primary memory as your computer's immediate workspace. It's the desk where it needs to access things super quickly to get active jobs done right now. But before we break down the specific components, we absolutely need to understand two critical concepts. The big dividing line here is the difference between volatile and non-volatile memory. Volatile memory is highly temporary. Literally the second you switch off the computer, everything stored there just vanishes. It needs constant power to hold its state. Non-volatile memory, on the other hand, is permanent. It remembers your data even when the plug is totally pulled. Understanding this distinction is absolutely crucial to knowing how our computers handle different types of tasks. Which brings us right to RAM versus ROM. Random access memory, or RAM, is volatile. It's that active workspace where the computer is constantly reading and writing data while you're in applications. But because it forgets literally everything when you power it down, a computer desperately needs read-only memory, or ROM. ROM is non-volatile. It holds permanent, specialized data that just gets used unchanged over and over again, like that essential bootstrap program that tells your computer exactly how to wake up when you first hit the power button. But hey, RAM isn't just one single thing. We've actually got two main types here, DRAM and SRAM. Dynamic RAM, or DRAM, is built out of these tiny capacitors that actually leak electricity. Because they leak, they have to be constantly recharged. We're talking every few milliseconds, just so they can remember their data. I know, it sounds super inefficient, but it requires fewer physical components. That makes it incredibly cheap and allows for really high-density storage. That's exactly why it's used for your main memory. Static RAM, or SRAM, uses flip-flop circuits instead. It doesn't need that constant recharging, which makes it way faster, but it's also a lot more expensive. So SRAM is usually reserved for that ultra-fast cache memory we talked about earlier. Now, the evolution of ROM is actually super fascinating. Back in the day, standard ROM was set at the factory. You could never change it. If there was a bug in the code, you literally had to throw the whole chip away. So engineers came up with PROM, which allowed system builders to write the data once. But what if you need an update later? Enter EPROM. You could erase this one, but you actually had to take the chip completely out of the circuit and shine ultraviolet light on it. Crazy, right? Finally, we arrived at EEPROM. This version can be erased using a simple electrical signal while it's still sitting right there in the circuit. It's such a beautifully elegant solution for updating permanent memory. Let's shift gears to Section 3, managing traffic and embedded systems. Okay, so we know where active data lives, but how does it actually move around without crashing into itself? And where else is computing power hiding outside of just our laptops and desktops? Well, when data moves from one part of a system to another, you get a massive problem if the sender is pushing data faster than the receiver can take it. The solution to this is a buffer. Think of it kind of like a waiting line at a really popular restaurant. The data enters the buffer, which acts as a temporary storage queue in the memory, and it emerges in the exact order it arrived. It perfectly smooths out all those digital traffic jams. You know, it might actually surprise you to learn that the vast majority of computers in the world aren't PCs or smartphones at all. They're embedded systems. These are highly specialized systems built directly into manufactured items, everything from your microwave to your car's engine. Because they only perform specific functions, they can be mass-produced incredibly cheaply. And increasingly, these devices are being connected to networks. This is what's creating the Internet of Things, or IoT. It provides us with incredible convenience for sure, but it's also opening up a whole new set of technological challenges. All right, moving to section 4, secondary storage solutions. Now we're zooming out to the long-term filing cabinets. This is where your photos, your documents, and those massive applications live permanently. For decades, the absolute king of this storage has been magnetic media, specifically the hard drive. Inside a hard drive, you have multiple platters spinning together at incredibly high speeds. Tiny read-write heads float over these platters on a literal cushion of air, changing magnetic states to represent binary ones and zeros. But here's the catch. Over time, as files are written, deleted, and rewritten, that data can become scattered or fragmented all across the disk. That forces those mechanical heads to work a lot harder, which eventually degrades your performance. An alternative to magnets is optical media, things like CDs, DVDs, and Blu-ray discs. Here, data is actually read from one single massive spiral track. As the disc spins, a laser focuses on this track, bouncing off microscopic physical bumps called pits and flat areas called lands. A sensor detects the intensity of the reflection and translates those physical differences back into binary ones and zeros. And the tighter you can focus that laser, like by using the shorter wavelengths of blue light in a Blu-ray, the more microscopic pits you can pack in, which means way higher capacity. But let's be real, the absolute game changer today is solid-state storage, specifically NAND flash memory. This technology completely eliminates mechanical delays. There are no spinning disks, no floating magnetic heads, no moving lasers at all. Instead, it relies on vast arrays of transistors acting as memory cells, all connected in a series. Its defining feature is that it can erase entire blocks of data simultaneously, literally in a flash. It is lightning fast, incredibly durable, and highly efficient. And our final stop, Section 5, bringing data to life. So we've processed and stored all this data, right? But how does the machine actually output it back to us in a way our human brains can understand? Let's start with screens. Today's flat-screen displays, like LCDs, are made up of a massive matrix of pixels. But if you look really closely, each pixel is actually made up of 3 subpixels, red, green, and blue. By super precisely varying the voltage to liquid crystals inside these cells, the screen changes the polarization of backlight shining through, mixing those 3 colors to create the vibrant images you're looking at right now. This same fundamental concept even powers virtual reality headsets. They just feed 2 slightly different paired images to your eyes to completely trick your brain into perceiving a 3D environment. And what about physical, hard copies? Guys, laser printing is literally a magic trick of static electricity and heat. First, a drum is given an electrical charge. Then, a laser beam rapidly scans across it, discharging very specific areas to draw an invisible electrostatic image. Then, charged toner powder is applied, and it only sticks to those discharged spots. The drum then rolls over a piece of charged paper, transferring the powder. Finally, heated rollers melt and fuse that toner permanently into the page. Wow, okay, we have covered a ton of ground today, from the hidden inner workings of memory all the way to lasers melting plastic onto paper. But I want to leave you with a thought connecting back to those embedded systems we talked about earlier. We are putting networked computer hardware into literally everything right now, from our refrigerators to our thermostats. And because they aren't traditional PCs, they're often way less protected. So as you look around your home today, I want you to ask yourself, just how secure is the embedded system inside your favorite smart appliance? It's definitely something to think about as our physical and digital worlds just keep colliding. Thank you so much for joining me on this explainer, and keep asking questions about the hardware that shapes our world.